All right, everybody, welcome to the last section of chapter 5, 5.7, which, as I mentioned in the very short section in our notebook, this is pretty much it. There's not a whole lot going on. There is one definition with 3 different parts, and that's it. Other than that, we'll see a few examples and then move on to chapter 6. All right, so this final section, nice way to finish, wrap it up, very short. And of course, when we see things that look like this, we want to know what it's equal to. And if you can't guess by the name of the section, I'm going to simply give them to you right now. I'm not even going to derive them because these are things that we will see in the future, but even then, not a whole lot of. All right. So this section is all about integrals that give us inverse trig functions. I know. Yes, here comes trig again. Right. So I know I had a few of you for that. You better know these, but everyone else, hopefully you recall them as well. If not, you may have to do a little bit of reminding of what is what. And the way that I taught it was not the unit circle, but with what are called reference angles. Okay, both in degrees and radians. Typically, we're going to be working with real numbers, so we will use radians opposed to degrees. Okay, so if you see something that has a fraction and square roots in the denominator of something that you are asked to take and integrate or find the antiderivative of, as long as you have something squared and something squared, or 2 perfect squares down there, the result is the inverse sign of that, which we are calling u over the absolute value of a, meaning it has to be the positive, not a negative. And because it's an indefinite, it's not defined over some interval, we are just finding the antiderivative, and we will not be actually evaluating from some a to b, which, by the way, is different than that a, so just don't get those confused. All right, we will also hopefully be able to do that, which means at the end we will have this, and we will use that fundamental theorem of calculus part 2. All right, but since we don't see that, we got to make sure that we put the plus c at the end. And that's it, my friends. That is the first of 3, that when you see a square root in the denominator with 2 things that are perfect squares, this is the one that you will go and look up and utilize. Now, keep in mind, I did put u's here. What do we prefer to be there? Not another function, but that's right, Dustin, just x would be preferable. And if it's just x, then this is just x and you don't have to stress. But I'm trying to give you the one that's all encompassing, because as you know, it's not always going to be just x. So we may have to do a little u substitution to figure out what those are. And the easy thing is, it's going to be that every single time. All right, so I'll give you some examples in a minute, but yeah, that's it. Part B, very similar, but instead of the difference of 2 squares that has the square root on it, what if we had addition of 2 squares? Well, for that one, it's actually going to be tangent. But it's also going to have a fraction of 1 over a times that arc or inverse tangent of this one is also u over a. But because everything's positive here, we don't have to worry about any absolute value. And because it is an indefinite integral, we don't see what we're trying to integrate over or from, then we are going to put that possibility of plus c. And the third and final, we got one with sine, we got one with tangent. We're going to need a reciprocal function in it as well. And this one is kind of like a combination of the two, but notice the order is changed. Instead of a squared, which a just represents some number, where u is the unknown, notice they are flip-flopped here. And in addition to that, it also has that u on the outside. So for this one, pretty nasty. It's kind of a combination of the two, but mix and matched. It's also going to, and again, because we have the negative, we're going to put the absolute values around the a. That fraction out in front. But this one is secant. And do you guys remember what secant is the reciprocal function for? Read it from right to left. It pretty much tells you. It looks like cosine. All right, so you're going to be thinking of the reciprocal or flipped fraction of what cosine would be. Right, and that would be of the absolute value of u over a, and again, plus c. Okay, give you a second to jot that down. Looks like I'm scaring a few of you off with this. Again, it's not me, it's you. No, I'm kidding. It's the calculus, and unfortunately, the way that these work out. So whenever you see square roots in fractions, or a fraction with perfect squares in the denominator, then you're going to want to go and look these up to see, hopefully, it matches the criteria that you were given. And then you will just replace it with this. And of course, if it's a definite integral from some number to some number, then we will evaluate it by plugging in the b and plugging in the a and subtracting our capital F of b minus capital F of a for those antiderivatives of the function given. All right. So again, that's it. Don't worry about memorizing these. If you do, more power to you. You got a quicker way to get to the end where others are going to have to look them up. Okay, so I didn't want to just leave it at that. I actually want to do an example of an indefinite and a definite. So I highlighted the two that I'm going to do of your 4 in each. You guys cool with that? Didn't think you would mind if I did one of your example problems. So which one does this look like here?
First one.
Very good. It has a square root and it has nothing on the outside. So I'm thinking it looks like the first one. So all I'm going to do is I'm going to write right underneath, this is my a squared, and this thing has to be my u squared. Now it's not just x, like Dustin had mentioned we would prefer. So that means we just found what u is, which means up top we need our du. Okay, does everybody understand what I'm trying to accomplish here? I'm trying to make it look like this. And unfortunately, I do have the dx up top, right? But what I don't have is just the x there for my u's. We actually have 16x squared instead of just x squared. Does that make sense? So that's why I'm trying to make it look like this. So going back to my problem, blow it up here so it's a little bit easier to see. Well, not too much. Then what do I have as my u?
4x.
Good. Because if that's what I put in here and square it, that's what would give me this. So I will be able to rewrite this as u squared down there if I let u equals 4x. Now remember, forget about all of this. Just like you should have practiced on that previous section with substitution in 5.5, and then we used it a little bit in 5.6 as well with the exponential and logarithms. But 5.5, we said if this is what we're calling u, forget about all of this up here. What would I get if I took the derivative of u with respect to x?
4.
Close.
Times dx.
Ah, good. Just like we talked about yesterday, Amanda. So since that is what I need, unfortunately, is that what I have up here, which is what I want only up top. I'm missing that 4, which is okay because I can multiply to get it. But I can't just multiply up here by 4 because that's going to give me something, what they asked for. That's going to be 4 times bigger than what was given.
Yeah, it's multiplied by the conjugate.
Not quite the conjugate,
Not
but I did.
the fancy one.
Good. Which means I'm going to also multiply by 1/4. Because if on the inside of my integral, I'm making it 4 times bigger, how do I undo that? I make it 1/4 as big. And so like Dustin mentioned, there's my fancy 1. And we know when we multiply something by 1, it stays the same. So I'm not going to make that jump just yet. I'm going to write all of this down. And I'm going to say, well, on the outside, don't lose it. You have to have it. I got 1/4 of what am I trying to integrate? Well, up top, what can I now write this as? Didn't we say that's equivalent?
du.
That's right. Very good. That's my du. On bottom, we have the square root that we can't get rid of, but I can rewrite that as a 1 squared minus a what?
U squared.
Good. And I'm not going to literally write the a or the u. Those are just placeholders for our values. Now, does it look like my du over a squared u squared? Great. Then let's actually do the integrating, the antiderivative of that. Go look it up. What is it?
Don't you still need the 4 on the top?
Nope. I rewrote the 4 dx as what it's equivalent to, the du. So I replaced this with the simpler version of it.
So then shouldn't you do that with the 4x?
Sure. If you want to, I just am going to end up replacing it back. So good point. If you want to call this a, you want to call this u, you want to use the, all good. All you need to recognize is that this is my u and this is my a. Because then we look it up and we say that is equivalent to the arc or inverse sine of what?
U over the absolute a.
Good. And what is u?
4x.
And what did we find the a to be?
1.
Which is always positive, so we don't need the absolute values around it.
Plus
Oh.
c.
Very good. I didn't sneeze. You said bless you or plus C?
Yeah, both work. I don't know.
That's right, Caesar. We need that plus C. And now here's one thing I was talking about with Amanda yesterday when she came by the office to get a little bit of help with these. When we take the 1/4, and technically we did all of this and got all of that, we should actually be distributing that 1/4 to both of these, right? But what does the C stand for?
Any constant.
Any constant. And what happens when you take that number, that constant, and multiply it by 1/4? What is it still going to be?
Any constant.
So therefore, what are we just going to leave it as?
See?
As in yes, C. We will leave it as a big plus C. Excellent. If you wanted to, you could, instead of writing the 1/4 out in front, you could put this whole thing over 4, but then some people will start canceling. Don't do that. Okay, that's why I put parentheses around these, so you know that that angle, which, because it's the inverse, it's actually my ratio, my y over my r for sine. I can't mess with that. So that is it. Little weird, little different, but same principles as what we've been doing since 5.5 and even a little bit before when we learned that fundamental theorem of calculus. Part 2 is coming up now. So again, I'll leave the other ones for you. And you can probably see that this is similar to that. So that will be an inverse sine. This one will be a what?
Arc tan.
Good. An arc or inverse tan, as they both said. And this one, the secant. So hopefully you can see I gave you one of each. I'm just doing one with you. Now let's do a definite integral. And as you can see, every single one of these, as you can see, you don't need the C because it has the A and the B, the upper and lower limits that we are going to integrate over. Which, remember, what does that mean we're actually finding? What does integrating mean?
The inverse of the derivative.
Good. So it finds the antiderivative for us, but it also means it gives us over these intervals
The area
the area
under the curve.
That's right. These curves. Just trying to hit that point home again because we did it so much with the derivative in chapters 3 and 4. But then in this chapter 5, I want to make sure it's not as much. The chapter is much shorter and it was only 1, where chapters 3 and 4 were the longest chapters that we did. And it was obviously 2. Okay, so again, the antiderivative, but it also finds the area under the curve if it gives you that upper and lower values or limits, we call them. Okay, so you guys cool with doing this one, or do you want to do a different one? I don't want to do this one. I want to leave that one for you guys. You want to do A, B, or C? I don't care.
C is fine.
Okay. No wonder C, sir, likes it. All right. So what are we going to do here? Well, we're going to try to integrate. And if we see perfect squares or roots in the denominator, now we're thinking, okay, it's one of my inverse trig functions, either sine or secant if it has a root in the denominator, or if it doesn't, it's just perfect squares, we're thinking inverse tan or arctan. So what I would like to have is, oh, sweet. This is exactly what I like to have. It can't get any easier than this, right? Because if you look back at what I gave you du and then a squared plus u squared. Because I wanted to give you the generalization, not just the exact way when there's only an x. But for this, it's perfect. We can just do the antiderivative or integrate this. So careful. What is your A? What is your U?
A is 1, U is X.
So what is the antiderivative of that thing? What do we get?
Tan inverse
Careful.
1 over 1.
Good. Now, I just wanted to make sure that you saw it because it's not always going to be a 1 and kind of disappeared, but very good, Soraya. Then we will have tan inverse of.
X over 1.
Good. And again, we can not write that, but just so that you can see it, because this will, if it was a 4, now it would be a 2 here.
Then parenthesis over the entire thing, and then root over 3 in the top and 1 over root 3 at the bottom.
Good. We don't need the plus C because that constant would end up canceling out when we do the fundamental theorem part 2 and subtract. The first C would cancel with the second C, so we're not even going to write it. But we are going to put a root 3 here. And do you guys like how I wrote 1 over root 3? Do we typically like fractions that have a root in the denominator? So what is that equivalent to?
3 to -1/2.
3 to the power negative 1.
Root 3 over 3.
That's what I was looking for. You guys said something that was correct, but unfortunately, we don't like 3 to the -1/2. If I'm going to plug that in, I don't know what that is either, even though it's correct. It is a different form. So we're just going to multiply this by that fancy 1 again to get a root 3 over 3. And hopefully you recognize that a little bit more with tangent. Okay, it's not necessary to change it, but that's how I know my trig. So I'm going to write it like that. So normally we would have been done. If it was indefinite, we would have just put plus C and cleaned up our ones and our fractions and all that. But now we have to put this in place of X and this in place of X. Which means I'm going to end up having the inverse tan of root 3 minus the inverse tan of root 3 over 3. Everybody good with that step? Because here comes trig to bite you in the behind. Everything up to this point was all calculus. Now you need to know what this means. And then hopefully what this is. Obviously that means inverse. We've been saying it over and over. But what does the inverse mean in math? All of math?
The
Opposite.
reverse.
Ah, very good, Jeremiah. Careful. This is how we say opposite in math. And again, these are oftenly confused in reciprocal, conjugate, reverse, inverse, opposite. All of those people just use loosely and synonymously. They are not. All right, so you need to know that this means that we have reversed our input and output. And with trig functions, what always follows a trig function? If that's not there, an angle. And because we have taken that ratio of y over x and reversed the input and the output, because we've done this, then that means this part is what they're giving us. So whenever you see the inverse, that means you're trying to find the what?
Angle.
And because degrees are kind of weird, we're going to keep it real in here. We're going to use real numbers, which means we're going to be using radians. And do you know the angle for tangent that gives you a root 3? Or the angle for tangent that gives you root 3 over 3?
like 60 or 30 degrees, one
Okay.
of those.
It is one of those. And which one? Well, you got to remember that this one is smaller. 3 times smaller. So this is my 30 right here. Because this is root 3 and this is root 3 over 3. So your 30, or how would you write that in radian measurements? Do you guys remember?
Pi over 6.
Jeremiah, excellent. Who is your trig teacher? You know this stuff really well.
Can I just put it in my calculator and get the answer? Like,
You took away my thunder, Soraya. His trig teacher was me. Okay. Yes, Soraya, of course you can, as long as you know how to use your
I mean,
calculator.
I did it like 5 minutes ago. I was like, okay, I'll wait. I'm kidding.
Just don't forget how you finish. Get a common denominator when you're subtracting fractions. So you're going to multiply by that fancy one more time. And get 2 pi over 6 minus 1 pi over 6 to get an answer of pi over 6. Which, oh, by the way, what does that represent? Let's make sure we understand this stuff well. What does pi over 6 represent? What did it just find for us?
30 degrees? Or what do you mean?
Exactly. What do I mean? What did
What's
you
your
guys
question?
just
Is it better?
do?
The angle.
No. And that's why radians are more powerful than degrees. They can represent a real number, just like pi. Before you ever learn trig or calculus or pre-calculus or any time you've seen and used pi, what was pi always equal to you?
Just more than 3, 3.14, etc.
Well, guess what? It's still that. But once you learn trig, you're like, oh, that's 180. And 180 divided by 6 is 30 degrees. No. What did I just remind you all that this finds for us?
The area?
The antiderivative, but very good, Caesar. We said if there is a window, an interval, we're actually finding the area under whatever that graph would look like. From there to there. Now, again, let me write it in a way that you would actually see it. If I rewrote this as 1 over 1 plus x squared times dx. Do you remember how we did the Riemann sums and we just cut a bunch of rectangles? In those rectangles, we knew the area was the length times the width. Do you see it now? All they did was smash this up top and write it as one big fraction. It's still finding the area under the curve from there to there. A very small window. And what did you guys just find it is about? Where did I get 1/2 from? Well, what did Dustin just remind us that pi was about?
3.
A little more than 3, right? It's 3-ish. So if this is 3-ish over 6, then we know it's half-ish. And why did I put units squared? Because we are finding what again?
An area.
And that is my perfect segue into the last section. All right. So just 3 of each type for you to do. The definite integrals and indefinite. Any questions on that before we move on to 6.1?
Why did you want us to do part D and not help us with it?
It's not bad. You just need to know secant, which you said, oh, I could just use my calculator. I had it 5 minutes ago.
Okay, I can do it. That's fine. I'll get
Yeah, good luck, because your calculator doesn't have secant, does it?
it. My trig notes does. So.
Ah, good. Just remember secant is just 1 over cosine.
Yeah. Okay.
All right. So just to let you know what chapter 6 entails, just 3 sections in this course, right? Most second semester calc teachers actually start back at this 6.1, 2, and 3 as, hey, remember these? Because if you don't, how are you going to do the rest of chapter 6 and on? Okay, so the good news is you will probably see these again. The bad news is I am going to test you on this stuff. You need to know it.
You need to add 6.2 and 6.3 to the module because we can't download and print the notes if we want to.
Correct. As soon as I finish writing them, I will post them. Yep, I'll have them done before Monday for sure. Thanks for the reminder, though.
Yeah, I just noticed because I went to go print them, but I only found 6.1.
Yeah, appreciate it. So because this is a brand new chapter, it is going to be a little lengthy. All right, but let's fill in the blanks. And of course, if you don't have it printed out or you don't have it accessible where you can just upload it to a tablet or anything, then I am recording this. You can write it down at the end when you watch it back. All right. I'm going to try to move through this quickly so that we can get to the actual finding of what we're doing here. But I wanted to let you know that now that chapter 5 is done and we learned about what integration is, which remember is 2 things, the antiderivative, and more importantly, what does it find for us when we have an interval?
Area under the curve.
I'm just going to get like something that I can push a button and Caesar just says that. All right. Area under the curve. Area under the curve. That's right. Okay. Now we're going to learn how to find different applications of it. And again, we're just going to scratch the surface with these first 3 sections. All right. So this first one is going to be the intro to it all. And then 6, 2, and 3, which we will do next time, that will be more of the application to the real world. All right. We'll get there.
It looks like we're just finding 2 curves and then subtracting one from the other.
That is exactly what we're doing. As you can see, I wanted to give you the visual, not just the verbal. All right. So just as a reminder, integration finds the antiderivative for us. But if we have an interval, a beginning and an end of that curve, that function, then it also finds
Area under the curve.
You sound different, Caesar. Very good. The area under the curve. So what we are going to be looking at is now 2 functions, not just one function, and trying to find the area between them. So as Dustin mentioned, when we take these 2 functions, we're going to always take the upper function, call it f of x, if you will. And if from A to B, I found all of those rectangles, those Riemann sum limit integration process, that I cut it up so many times, you didn't see any gaps. Then is that what I want now? Do I want from A to B? Do I want all of this area under the curve?
No.
What do I actually want to do? I want to remove that part. And how do we remove things in math?
Subtract.
And if we subtract, what are we going to be subtracting?
Subtracting the g of x area from the f of x area.
We're going to subtract off the area under the lower curve. And if we took all of this and subtracted off that, look what we're going to be left with. The area between the curves. Okay, so we're going to be learning not only what we're doing, we're obviously, once we figure that out, going to learn how to do that. And I just explained both of those to you right then. Okay, this is super important for you to conceptually understand. This is very, very important, not just this, which most people want. Because they just want to get it over with. How do I do it? I'll do it. Stop talking. Go ahead, Sarai.
So after we learn this in the test, are we still going to get questions from 5.1 to 5.4? Like, because it looks like the same thing, except we're just trying to subtract two answers. So, I mean, 5.1 to 5.4 looks just redundant after this.
Yeah, no, that's a great comment, great point, and you're absolutely right. Now, why might I have you find a Riemann sum from the left or right? Just so that you understand, just like we did at the very, very end of chapter 2, which was our limit chapter, and we talked about that slope formula we called the difference quotient. That was the fancy way to write it. And we took the limit as it approached infinity and we called it the derivative. Well, do you even remember that? Do you understand that the derivative was just the slope formula? At a specific point when we took those 2 points and made it 1, that's the reason that I want you to understand that the difference quotient, the slope formula, was so important. It's the basis of this whole class. Well, then, yeah, I'll probably give you a Riemann sum for the same reason, because that's what is the basis of chapters 5 and 6, or this thing we call the antiderivative and what it finds for us. Yeah, great point. And what do I mean by great point? What does she just kind of tell you is going to be the majority of the test? I'll let you guys figure that out. Okay. So this thing right here is actually super important. And you're like, it's just a rectangle, bro. It's just a rectangle in between those two curves. But notice that that rectangle changes all the time in size. And when things vary or change, we have to use variables. Because I don't want to give away too much, but the next section, or sections 6.2 and 6.3, we're going to actually take this flat two-dimensional area and we're going to put a little spin on it. We're going to rotate it around either the x-axis or even the y-axis. And that is now going to take our two-dimensional thing and make it 3D. And I see some of you already have your glasses on. You'll be able to see it better. Yeah, it's going to be a little different. So make sure you're here on Monday if you can be.
Wait, so if it's 3D, this curves, like, do they end somewhere, or are we like trying to find infinite areas?
Right?
Yeah.
We're trying to make as many cuts as we can, but from A to B, some interval.
No, like if it becomes 3D, like if we're trying to work towards like the vertical axis, so this like fx and gx, are they going to end somewhere, the curve, like, or is it just, are we just trying to find infinite area, like just an approximate area? Then
Yeah, because with the third axis, we're going to need a third or second, an additional point.
There's not a third axis. It just makes it solid.
So it's eventually a sphere that we're trying to find the area for.
Ah, very good. We'll get there. There's going to be all different types of scenarios where there's a hollow middle, or it can be solid if we're going from 0 to B. when we spin it around that, it will be solid.
I mean, hollow still makes sense. We could find the area for the solid and then the hollow and then subtract it, I guess.
Which is exactly what we are introducing with this.
So a donut.
Do
Exactly.
the spinny thing.
What'd you say, Amanda? I'm sorry.
Do the spinny thing you showed me.
Exactly. Yep. Yep. When I'm in person, I actually bring my drill. It wouldn't have the same effect here, but I bring my drill and I have a pencil put in it and I have a shape, a 2-dimensional shape, piece of paper taped to it. And then what I do is I actually push my drill on and it spins it around really fast. And what happens is now you'll start to see that solid. And I turn it both directions so that you guys can see what it is. But that's virtually what we're doing, whether it's along the x-axis or the y-axis or some other horizontal or vertical line. But let's pump the brakes a bit. Let's make sure that we can do the area between two curves before we start spinning out of control. All right. So the next few things, we're still going to be having that fixed width we call delta x. But in integrals, we change it to dx, right? In calculus. So it's still going to be that fixed width for each one of those. So that's nice. But what is going to change is going to be the heights of both functions. The cool thing is the width will be the same, so it's like we factor it out. But the heights of each one of these is going to be different for both f and g. And because those vary, we're going to have variables. So we're not going to still, as Soraya mentioned, do we really even need, those Riemann sums when we're going to cut it up infinitely? No, but I still want you to understand they are Riemann sums. And as long as your f function is greater than or equal to your g function at all the places, then we know that this is the upper and this is the lower function. And therefore, what are we going to do to find the area between them? We will take the bigger and subtract the smaller so that we get rid of or delete that bottom part and are only left with the area between that we wanted. Okay, so to generalize this, we're going to take the top function and subtract the bottom function. And because we're going to use that Riemann sum special way we call integration, if you know how to subtract these things, then do it. Because ultimately, what are we going to have to end up doing with this? Integrating it, finding the antiderivative from A to B, which means that fundamental theorem of calculus part 2. To find what? What are we finding? Now,
The area between the curves.
I have it. New button. Very good, Caesar. Now it's the area between them. Excellent. Pretty awesome. But you know it doesn't always work out perfectly. What do I mean by that? Look at the next page. And look at 2 example graphs that I gave you. Similar looking, one with a cubic, it looks like a cubic function, or even cosine. and a line with or without slope. If we were trying to find the area between the curves, let's say this one from 0 to pi, do you guys see how it's a little bit more than 3? As Dustin mentioned. Then this from 0 to 1, do you see what my upper function is and what my lower function is? But from here to here, the rest of it, they flip-flopped. So what do you think we would do in order to try to find this area between the curves?
Do
Well-
it from 0 to 1 with cosine being the upper bound, and then from 1 to over 3 with g being the upper bound.
That's right. We would have to split it up and add two separate. One from 0 to 1, where it's this minus that, which they're just telling you it's up at a half, our y value is for each of these. All right, cosine theta and my other one, g theta. But then the other one, it's flip-flopped. Now my upper one is this, that I would find the area under the curve, and then I'd subtract. Now you're looking at that and you're like, well, we actually need to add, don't we? But what kind of area is that if it's below our x-axis? What kind of y values are we going to have?
Negative.
And what happens when you subtract a negative?
You flip the x values.
It ends up getting positive. So the cool thing is you don't even have to think about it. It's always going to be the bigger one minus the smaller one. So yeah, for that one, we would go from 1 to pi, but we would have the 1/2 minus the cosine theta. And again, if those are our heights, we still need our width. Does that make sense? We're going to have to sometimes split these up and add them together because it flip-flops from which one is the upper and the lower at some point within our interval. This one, same idea. To find the area between, we'd have to split it at 1 again.
So say we did something very similar, and I think it was a 5.3 or 5.4 homework online.
That's right. We went from A to C. Right? Or a lot of times they just use B. And then we would actually split that up and actually go from A to C and then add it from C to B. And we said that those are equivalent statements. Excellent. So what is a way that we can do this without having to graph and thinking, okay, well, where is it and what is all that? We're going to do the absolute value of the difference. Now, how do we know which one is above and which one is below? Well, you don't have to graph them to find it. You can use the absolute value. Here's the problem. Do we know how to integrate an absolute value? No. So as Dustin was kind of mentioning, we've done something like this before. What are we going to do with the absolute value? We're going to see where it's 0. Because what is the definition of absolute value? Anybody know? It's 3 words. Distance from 0. That's what the absolute value means, which is why everything always comes out positive. Whether you are a distance going to the right 3 or to the left 3, a distance of 3. So therefore positive. So the first thing we are going to do is we're going to take that thing and figure out where it's equal to 0. But that only tells us where they're the same, where f of x is equal to g of x, right? That's the only way that they'll be 0. So what else do we have to do to figure out which one is above and which one is below? We're going to do just like we did way back in chapter 3 and 4 when we were finding derivatives and finding how to use them. And then chapter 4 with our first derivative and second derivative stuff to see where it's increasing or decreasing or concavity. Go ahead, Dustin.
So then we're going to be finding the relative mins and maxes.
Not really, because remember, this is the antiderivative.
So
Not the
then
derivative.
were their inflection points. Well,
We-
wait, no, antiderivatives. So it's not either of those. It's just, okay.
Yeah, we don't really know what these functions represent. Was it a second derivative, a third derivative? But remember, we are going backwards. So relatively speaking, no pun intended, we don't know if it's any one of those things. All we know is that this is the antiderivative of that, which finds the area under the curve for that.
But we're still concerned about where it's going from positive to negative or negative to positive.
Because if I took f of x and I subtracted g of x without the absolute values, and this was not the case, then what would it come out if g of x was actually bigger than f of x?
Negative.
And how are we going to combat that?
Absolutes.
We will throw a negative on the outside to get rid of the absolutes. Very good. So this, my friends, is just our shortcut. To not having to graph and to not have to really figure out what is above and what is below and where. This is our algebraic way rather than having to use geometry in seeing which is above and which is below. Okay, we're going to find where they are the same within our interval. That is where it will equal 0. Right? Because the f of x and the g of x are the same at that point. So if you subtract f and g, you will get 0 because they are the same. That's what this is finding. Here, here, and here. And as long as any one of those points is in our interval, what are we going to do? We're going to split it there. And we're going to say if we're going from 0 to say 2, then we would split it right at 1. But how do we know which one's above and which one's below? Well, if this was f and this was g, then what are you going to get in your sign chart about 1? You would get positive when you did f minus g, because f you can see is bigger than the g is. What would you get to the right of 1? Well, now g is bigger than f, isn't it? But because we did f minus g in all of this, what is it going to come out? Negative. Because we're still doing f minus g because we don't want to guess. We're just going to do it. And how are we going to combat that so that it does give me the correct thing? We're going to use that sign chart for anywhere there is a negative. However many zeros we get, right? If it goes positive, negative, positive, what are we going to do within that interval? if let's say this is my interval, A to B, let's just call this, instead of just 0, let's call them something. Let's call it a C and a D. Then we would have to split this up into 1, 2, 3 different parts.
We're going to be looking for the area underneath the G and above the F function.
And remember, we're still finding the area between them. So not just that, we are going to have to take all of it, and subtract off the other so that we just get that. But in order to know that, we need to know which one's above and which one's below. And we don't want to have to graph these functions. We already see that they're pretty ugly sometimes. So this is our way of doing it without having to graph. We find where the zeros are, and we split it up and test to see whether it's positive or negative. And if it's positive, then guess what? We already got our F minus G, we're good. But if it's negative, like it would be from here to here, what would we have to do, since that is the opposite of what we did? F minus G?
Put a negative in front, like you said earlier.
Because what would that then ultimately do?
Make it the absolute value.
It would make it G minus F. Do you guys see that?
Okay, so then that, looking at it graphically, for if you can scroll up,
Yep.
that portion that's negative is the portion that's underneath the G line, right?
Not necessarily. It's a good point. It's not necessarily just that. It's because we are going to try to streamline this process and always just do F minus G. I want to know if that's what I should have done. Here, yes. Here, yes. If I take the area under the curve for my F, all of it to the x-axis, and I subtract off the area under the curve from G, then I will be left with the area under the curve between them. But if I did the F minus G from 1 to 2, that's not going to give me the correct thing, is it? It's going to give me the area under the curve to the x-axis here minus here, which is ultimately going to give me what I wanted, but it's going to be the what?
Opposite.
And what symbol that you actually helped us with earlier, we will use to combat that is the negative. Because in reality, we wanted the G minus the F. So we want the opposite of that. And if you throw a negative out in front of it to get rid of those absolute values, distribute the negative, now your F is negative and your G would become positive. So you see, it does the work for us. But how are we going to know without graphing these functions? We test. We test about the zeros, the places where they are the same within our interval. We don't care about anything outside of our interval. So only from A to B. Okay, and I know this is weird. I'm trying to go very slow with you all. Luckily, it's not just the video of me talking to myself, and you guys can ask questions. But there is a third scenario, unfortunately. We went over the first one. That is the second. When it changes, which one's the upper and the lower? But you might be asking yourself, why? Why is it necessary? And you're absolutely right. Because sometimes it only makes sense to use the y-axis, not the x. And that's weird. And it's like, dude, we're just getting started with this. Why are you going to do that? Unfortunately, guys, I'll give you an example of why we will be using the y-axis. Some of these you can't do it without it. Let me show you visually what I mean. Take a look at these two examples. And then we'll fill in those blanks. Now, obviously, you can see that first example here. Our upper function is just f, and there is no lower. All right, so we would just be finding this. But then we'd have to split it up and do another where it's just the area under this function now, the g. And do we like doing two integrals? Or would you rather do one? You're like, I don't know, that seems pretty easy. And you're right. But you won't always be able to do that. What if I wanted to find the area between these two curves with this sideways parabola, so x equals y squared instead of y equals x squared, and this vertical line, x equals 9. Now we're looking at this. And if we were only able to use our x-axis and our little rectangles with our width of x, then how would we do this one? It seems like this is irrelevant almost, right? Now, if you were smart, you'd say, well, I know how to find the area under the curve of this thing to the x-axis. And because we know parabolas are symmetrical, then I could just double it. And yeah, you'd be right. But what if I shifted it up, down, or moved it around? That's what we're talking about. Okay. I know there's always special circumstances, but we want to generalize this. So what if I did this? You guys ready? Check this out. What if I was able to draw a representative rectangle, we're going to call it? What is the width of every single one of these rectangles now?
Not the same width for sure.
Now, again, I'm just trying to draw it freehand, but what would they all be if I could make them all the same width? What would the width be?
I could have the same length or width, and my x values will become my length.
That's right. So if we're trying to find the area of a bunch of rectangles, it's still length times width. But now my length, as Sarai is mentioning, are going to be based on how far to the right I'm going, not how far up I'm going. So it's no longer our f minus g for our y values. It's going to be our x's that's changing. And what's not going to change then is those y's. So the way that we're going to draw these out now, and again, I made a little joke, as I sometimes try to do. Doesn't always work with you guys, but just because something's comfortable and we can always work with the x's, doesn't mean it's always wise. So we're going to change from all of the x values that we've been working with, and we're going to change it to y's. So the good news is everything that we've just talked about in those first two scenarios is still going to be the same, but instead of writing this as the area between f of x minus g of x dx from 0 to 2, which I would have had to have split to find from 0 to 1 and then 1 to 2, we can also rewrite it as the area from 0 to 1. But that's along the what axis?
Why?
Which means now I'm going to be using g of y as my, if you just kind of tilt your head, everybody, go ahead, do it. Tilt your head to the right. Come on, just do it. And look, when you do that, now you have your x-axis here and you're looking up that way. Just like we've always done, but now it's our y-axis that we're looking at. And this one would be my upper or bigger. And this one would be the lower or smaller.
So if I tilt my head, will my equation also make x the subject and y the variables for it?
Unfortunately not. You're going to have to do that on your own. But yes, Soraya, you will be able to see it a little bit better when you tilt your head, but you're going to have to do the work and write your g and your y, f function in terms of y, which means if this is our length, we're going
Respect
to
to
need
dy.
our width to be also in terms of y. Now, this is more of a formality than anything. All the work is right here, isn't it? But this is the key to letting you know what these should be in terms of. So that's why we draw this, what is called a representative rectangle. So do me a favor, everyone. See if you can set this one up for me. See if you can draw that one out in terms of how you would solve it. All right, I hope you got that. Let's take a look. Now our representative rectangles, so that we have one minus the other, right? We want to get rid of all of this area here and this area here, which if you notice, that is the area under our sideways parabola. If I find the area of all of this from what looks like what?
3 to negative, or negative 3 to 3.
Good. Then I know from negative 3 to 3, I can take my whole area for this thing and subtract off that area to find, again, the area between those two curves. But if we're using the y-axis, we need these widths all to be the same on those little rectangles that we're going to end up drawing. Not in reality, but theoretically, with that Riemann sum thing that we got rid of. So that means it's going to be dy. And therefore, everything that we put in there has to be in terms of y's. So again, we're not going to use the f, we're not going to use the g, but we are going to use them in their forms, which is nice because if you notice, they didn't write f of x and g of x over here. They already told you what x is equal to in terms of y for this one and this one. So you just need to know what your larger one is and which one you're going to subtract off for your smaller one. And so what should you have put first here?
9.
9
And we would subtract off what?
Y
y
squared.
squared.
And would you guys actually know how to integrate that? Let me rephrase that. Should you know how to integrate that? Yeah.
Just substitution.
Now, do you see it? It's the same thing that we've been doing. You don't even need a U sub. You know how to integrate this as is. What is a constant when you take the antiderivative?
9x.
And again, it would be y now instead of x. That's right. And then what is this? What kind of rule?
Be y to the third over 3.
Power rule. And we would be evaluating that from -3 to 3. Done. That's it. So again, a lot of the same thing that we've been working on for the past few weeks, but now with a little bit different perspective. Turning our head for turning our axis. All right, so all the notes underneath, that's exactly what we're gonna make sure that we understood, is that instead of going from 0 to 1 with x's, we could go from 1 to 2 with the other one, g of x, or instead we could look at from 0 to 1 and take the upper and subtract off the lower to find that area between the two curves. And get rid of the x's and use the y's. So to generalize, we will always take the larger function, whether that's the y value in terms of x, or now the x values in terms of y. Okay, it'll be the larger minus the smaller function. And how are you going to figure out what to use? The dy or the dx? You should draw what is called a representative rectangle, where the width is either that dy or dx. So if you scroll up a little bit more, you will be able to see exactly the same thing that we had in the very first scenario, when there was always a larger one and a smaller one in our interval. But now instead of it being the upper minus the lower to find the area in between, now it's going to be the larger minus the smaller, further right than left, and subtracting that off to find the area between. Just got to make sure that everything's in terms of y. Okay, so what could you help yourself in doing for every single one of these? You could draw it out. Now, some of these you will know. Some of them you may have to use a computer program, graphing calculator, Desmos, whatever it might be, in order to graph. But the nice thing is, are we required to graph? All these formulas to find the area between the two curves are set up to help us. And if you had to only have one thing in your notes for this entire day, it would be this one. Understanding that we don't know how to anti-differentiate or integrate an absolute value. So we find where it's equal to 0 and test around it. In any place that it is negative, all we do, instead of adding from A to B all these different sections or intervals, to combat the negative, we throw a negative on the outside to make it positive. That's the gist of it. Of course, in order to understand it, we got to put it into practice. So just a few problems, 3 total. That's what we'll work on the remainder of the time.